device, you have a bunch of functions. Yeah. Yeah. So like on like the Intel most PC chipsets, logically, internally it's just all some proprietary bus, but logically, I think like everything in the Southbridge is like device 31, but then everything inside of it is like they use up all the functions possible. So for like LPC, SATA, USB, and all that stuff. So for Intel, the modern platforms between the CPU and the chipset, it's a thing called DMI, which is electrically it's PCI Express, but logically it's Intel's own secret thing. But then from the Southbridge, you have a few PCIe lanes, and all the devices there appear to PCI software because PCI software has been around for like 2 decades now.
So what's next?
What's next here?
What's next for PCI?
They're talking Gen 4, which is supposed to go to 16 gig transfers per second over copper, or so they promise, and that's due in like a year or two, or so they claim.
The footprint of Alpha 10 probably.
Yeah, exactly. Yeah, and they're hoping there should be no change, like the same add-in card connector and the same everything, just obnoxiously fast.
No silicon photonics yet, huh?
Yeah.
Yep.
Exactly. I'll just go into the Linux PCI stuff. It's actually not that bad, believe it or not, for Linux. So there's a guy called Greg Hartman who I tried to get here as a go, but I don't think they ever emailed him. But he's the guy who maintains the Linux PCI stuff. And thanks to the backwards compatibility and the structure of PCI space, the kernel, it doesn't know or care what the device is. It doesn't know if it's PCI, PCIX, or PCIe. Your BIOS is responsible for the initial resource allocation, not your driver, so all you're doing is flipping a few switches. So LSPCI, as people used it before probably in the course of debugging or messing around, it shows you your devices and previewing, hey, this one's actually readable. So this
Here it is.
Yeah, here it is.
Mistakes been made.
Yeah. But basically this is kind of showing, there's actually segments before buses, but again, no one ever uses that except for telecom folks because they're nuts. Then you have, bus 0, then we have our devices on this bus, and then dot the function number right here. And each PCI Express device gets its own bus too. So the bus numbers start shooting up real fast with PCI Express. So the driver anatomy is actually not that bad. I don't know if I want to go through slides or I just brought one. I can just open up Notepad now that I think about it. Yes, I do. I don't. Yeah.
Has that been
YouTube? Yeah, it's been like opening up in this like super tight thing, and actually, I think like if people read this or read it in 2 minutes.
Yeah, that was good.
Okay. So this is just like a little dummy driver, basically. So what you always start with is this table right here, which tells the kernel, I'm looking for any PCI device, and the kernel takes care of all this stuff for you in terms of collecting this data from devices, which is really nice. You basically say, hey, I want to find this device vendor, this vendor ID and this device ID. These are the subsystem ID fields, which I didn't care about in this case. And then I don't even remember what these are offhand, but they are important. So basically this is saying I'm looking for a TI DSP and a NetChip USB controller. And then I export that and say, hey, kernel, give me this whenever possible. And then I actually need to skip down to here. And this is the structure right here which describes to the kernel what my driver is doing. So I'm like, this is a test driver, here's my table, here's my probe function, and here's the function to call when my device disappears. So the probe function is what the kernel will call when it finds a device, like, hey, found a device, you're a handler, I'm going to call your probe function. So in this case, my probe function here is prefixed with dev init, which means that it's hot pluggable, so don't dump this out of memory immediately after you load it, whereas if you use it init, it would dump it out of memory, and you'd spend like 4 hours trying to figure out why hot plug doesn't work. So RTFM. And in this case, all I'm doing is calling PCI enabled device, and this single line right here then just tells the kernel to go do a bunch of work, turn on memory, assign regions, and I'm just like, all right, done, my hands are done. And with that one command, the device is enabled, and I can start poking at registers and doing anything with it. And then this is what's called when you call insmod or modprobe. Basically, I'm registering my driver. When I call rmmod, I unregister my driver. And then up here, in my removal case here, I'm just doing PCI disable device, and that's it. this like little 40-line file right here is a PCI device driver, and your device is hooked up, and you can do whatever you want to it.
Is it similar configuration for like a USB device?
Yeah, the USB framework's a little different.
Okay, because I was wondering about if you wanted to do like a Arduino Leonardo and use that as an actual device, because that wouldn't show up as a PCI device. That
Well, so with, to be a PCI device, you need a high-speed serial transceiver, which no microcontroller will ever have, obviously, so. And then, I guess I can show this one too. In a little more involved pro function, this is for a FPGA-based CAN controller. In DevInit, I can actually say, hey, give me my memory address here, which I can then dump out, and then I can map, I can just literally call kmalloc and get some memory regions where I remap physical memory space to some kernel memory space. And then I can just literally start doing things like this where I just say, write V, and then it will write this out via PCIe to this device, and I can just say, hey, this right here literally just wiggles 2 I/O lines high to enable my device.
Now, could I also use the driver right now? I used to do that FPGA.
Yep.
If I wanted an initial software load into the FPGA from the bus, would I do this here, or would I do this?
So that's a little more, you can do it there, so a lot of the new FPGAs let you just flash new firmware via, or reconfigure the device while running over PCI Express. So one thing that we've been playing with is, we have a platform where people can plug in different I/O cards, and Linux will boot, check out what I/O cards are, and then reconfigure different sections of the FPGA to talk to those I/O cards as needed.
Okay.
So I think that's documentation from Altera and Xilinx that tell you, hey, you have to do this register stuff, and they give you a little example program for that. And then down here, MSIs, you need to specifically enable them, otherwise your device is going to use the legacy interrupts. So then going back here, basically I just tried copying and pasting it here, but PowerPoint kind of murdered my formatting, but just kind of reiterating that you need your driver struct, there's predefined functions that are common to all drivers. Your general initialization flow is you're going to enable the device. By request resources, basically calling PCI enable device will have the kernel go out and turn on and set the enable bits in the command and status register to say, hey, your resources are now active, so whatever your BIOS handed you, you get. And during the 32, 64-bit switch, there were a lot of terrible buggy BIOSes out there that just did a terrible job assigning bars. You actually had to move your card to a specific slot to get it to work. So now it's not a spec problem, it's an implementation problem. You'd initialize device registers. You'd set up DMA. I just realized I didn't mention DMA. DMA. So DMA is direct memory access. So everything I've described so far would be PIO or programmed I/O. So your CPU is burning cycles, copying data from point A to point B. With DMA and like an Ethernet card, you can set it up. You just use the CPU to set up initially, and then DMA allows devices to directly dump data to and from main memory without ever bothering the CPU. So like for Ethernet cards, as you get frames and such, you can DMA them into memory where the driver then takes it and offloads it to your TCP IP stack. And that's, FireWire allowed DMA, so there's people worried about you can do a DMA attack on a device by plugging in a FireWire device and you get direct system memory, which is true, but practically I don't know how many people used FireWire or even did that, right? So set up DMA and then you register your interrupt in your interrupt handler. So you don't want to, if you screw up this part, then you get stuck in some infinite loop in your interrupt handler, maybe if you forget to clear flags or you just don't service interrupts. You register your device with any other subsystem, so if you have like a network driver, you do your initialization, then you let the Linux stack know, hey, I'm a network driver, what's going on? Or you let the USB stack know, hey, I'm a USB controller, and you just kind of register yourself there, and then you're done. And it's pretty similar on Windows for a lot of this stuff, except it's vastly better documented because MSDN exists. But I will say on Linux though, if something goes wrong, you have the kernel source code in front of you, which is really, really nice, and it's pretty easy to debug. Whereas on Windows, you need a separate box, and you have to use WinDebug with like a USB debug cable or something like that. And then just kind of PCI.h is the kernel space header file for this, and this just has probably a few hundred functions that you can use for PCI stuff. So you can do read and writes from config space with just a single function. You can request release memory regions, get resource links, and then it also gives you handy bit field definitions. So if you just want to check a specific bit in the register, you can just refer to it by name. You don't need to memorize any of the locations or numbers or anything like that. If you're interested in reading more about it, I think the Prentice Hall book is, I don't think there's a free version available, but I think the O'Reilly book is on lwm.net if you want to get that. And it's a pretty good reference. And then the kernel source, and I'm not even joking, the PCI stuff is actually decently commented for a change. So the kernel source is actually pretty useful. And then I guess a little bit of FPGA stuff. So the newer FPGAs have PCI Express hard IP even on the lower end stuff. So like an Altera Cyclone 4 GX you can get with hard IP on it. It's like $30. And obviously assembling is a whole different story. It's a VGA, but the chip itself is not horribly expensive. And by hard IP, it's implemented in the FPGA as dedicated silicon, whereas previously with soft IP, the device would have transceivers on it, but you need to consume resources on your device to actually use PCI Express. And with your FPGA, you can strap your application to PCIe for performance reasons. So custom crypto is really popular. Bitcoin mining. I know I purposely have it about coin mining. I think Bitcoins are silly, but Bitcoin mining, a lot of people use GPUs. There's that company Butterfly Labs that I think prototype on FPGAs and then actually spend a few $1 million making ASICs for that. If you have custom buses, a lot of industrial stuff, you can use this in Blue Logic. And high-speed, low-latency I/O if you're doing like hardware-in-the-loop simulation. You can do everything on the FPGA and you can close your loops in nanoseconds. So pretty fast. And generally what it does is the hard IP basically decodes the transaction layer packets and passes it through some vendor-specific bus to the rest of your code. So in the case of Altera, which I'll show you in a second, basically it decodes these packets. So all you have to do is say, oh hey, it's a memory read, and it gives you the address and the other parameters, and then you just literally say, oh, it's a memory read, and then your logic says, okay, here's the data back you asked for. And it's a memory write, you're like, oh, I'm going to take this data and put it here. So it does a lot of the heavy lifting for you in hardware. It makes it easy-ish to kind of to do that. So I couldn't find a pure motherboard for this card, but if you guys want to look at it, it's kind of static safe bag. This is an Altera dev kit with a PCIe i8 lane on it. I was hoping to actually plug it in and wiggle some stuff with it, but did not get around to that, but I can pass that around if you want to look at that. What I can show you actually is the wizard in the software that allows you to configure this. And I just skipped a little bit so it's ready to run. So this is so Altera Fortis is the design software for Altera FPGAs, and there's literally a wizard where you can say, hey, I want to make a PCIe core. So literally all you do here is PHY type. We'll say Stratus 2, and all the stuff's pre-configured for you. And let's say I want to be a by 8 link. Let's say I want to be PCIe 1.1, which in this actually no, that's not good. It's like 1.4. So let's say I want to be a by 1 link. Oh. There. By 4. Let's say I want to be a PCIe 2.0 device. I don't really need to test out with. And this right here, Joe's what you're talking about. This lets you configure, reconfigure the thing over PCI Express.
Okay.
And the transceiver block clocking, basically what FPGAs can do is they can use the reference clock as an input, and they can generate all their needed clocks from that ref clock. Everything comes down to clocks in the end, is what it, once this really crappy triple GUI stops freezing. No, let's skip past that. That never opened up. So here's where I set up my bars. So I can say, hey, I want to be a 32-bit bar, and then I can say, what's my bar size? So basically all this is doing is I'm telling it how many ones should it be hardwiring. So when the host writes and reads back, it gets this number. So I could be, I can consume an obnoxious amount of memory space if I tie them all to one. But if I was doing like just a little simple device, I'd be like, all right, hey, just give me a bag, and then maybe I want, or actually, let's say I just wanted a little space for my configuration stuff, so let's say give me like 4 kilobytes for just my housekeeping stuff, and then let's say this is some kind of like interface card to some custom bus, and that's like a 22-bit bus. Let's say give me, say, 8 megs, and this bar will point to some other region of memory. And then here I can program in my device ID, so I can say device beef from vendor dead. And then I can say next. And then this is all the low-level PCIe stuff where I can support tags and MSIs and all this stuff here. I can implement that if I wanted to, but there's no need for that in this case. And then maximum payload size is kind of interesting. So this is the maximum number of data bytes you can cram into a single like memory read, memory write packet. And the interesting thing is, I think the spec allows you to go all the way up to 4 kilobytes per transaction, but you're limited by the smallest device on the bus anyway. In most cases, that's going to be a 128-byte device. So a lot of motherboards will expose that option, and we'll be like, ooh, I'm going to change that. And it does nothing in the end, because the bus will automatically negotiate down. Because it's like, hey, you said you're 128, so we're limiting ourselves to that.
No, jumbo for you.
Exactly. And then, next again. And then literally, you hit finish, and now this thing is going to spit out a little PCIe core. You flash it to that board, and you have a very simple PCI Express device. And it will go through and generate all this stuff. So, but that's about all I had. Any questions, comments, ideas?
How far out with photonics and stuff like this?
They've been playing with like ICs that have like the transceivers right on the silicon die, and I mean they're used in like the really high-end networking stuff, like what this guy plays with all the time, and you. But like as for like entirely photonic chips, I think they're still lab rats for the most part.
So how accessible is this if I wanted to go out and get a card? Do you start doing that with $10,000?
No, actually, I think the Cyclone 4 RDK with the transceivers is like $800, I think. Xilinx sells the Z board, which is for their new Zinc thing, which combines 2 ARM cores and an FPGA on one chip. And they're talking about making and that's $300. They're talking about making a version of that card with transceivers, which means you could link it to PCIe stuff if you wanted. But yeah, I mean, it's pricey, but I don't think it's like crazy out of the realm of possibility. I mean, I feel like you could easily spend this much if you bought like 10 shields or something, like Arduino shields for like $30 a pop. The better question is, I just don't know what you use it with, so. Do you have ideas? Yeah. Custom software-defined radio stuff.
Actually, that's exactly what I was going
Yeah.
with, the software.
Yeah, and actually a lot of, if you're familiar with software-defined radio at all, a lot of them at their heart is just an FPGA tied over. Some of them are PCI, but a lot of them are FPGA to USB, or FPGA to Gig E, but the FPGA is doing all of the waveform generation and such.
I don't know if you might be a little too off topic, but DMA. If you have a device that has access to DMA and your software has control of that device, can't you read any memory from any process? Is that kind of a...
Yeah, it's only a security risk. And you know, depending on your host operating system and your memory controller, AMD or Intel, there's some protection you can implement. But a big fear in the early days was like FireWire is a port that's on the outside of your computer, and FireWire allows you performance reasons DMA. So theoretically, you could plug in a little device on a FireWire stick and dump out contents of memory at any location you desire.
But there are ways to implement protection.
I think so, yeah. In the OS.
You needed newer silicon, but like if you had a box from 3 or 4 years ago, it would be vulnerable.
Yeah, older
They're
boxes.
saying with epoxy firewall port stuff, but the new stuff, there's actually, especially some of the new virtualization extensions, there are hard.
Yeah, especially with virtualization stuff.
Yeah.
And there's a lot of PCIe extensions they've added for virtualization purposes too, that make it easier to do PCIe pass-through to host devices. If you're running like an ESX or ESXi farm.
Who runs the other?
What's that?
Who runs that?
Yeah, exactly. Yep.